Okay, in this video we're going to look at resistivity and temperature coefficient. So let's start off with our resistivity formula that was going to be given to us. So resistance is equal to the resistivity of some material multiplied by the length divided by the area. So hopefully it should make sense that if you increase the size of the cable, so the cross-sectional area, so you've got a bigger, fatter cable, then the resistance will go down. Okay, whereas a tiny cable, it's going to have a higher resistance because it'll be harder for the current to go down. And then the longer the cable it's going to be, the longer the cable, the more resistance we're going to have. So the further we have cables going, then the more resistance it has, whereas the shorter the cable, the shorter the resistance is. Okay, so let's put this into practice with a couple of questions. So in this first question, nice and quite straightforward, we want to find the resistance of the wire that we've got. So we've got the diameter, 0.58 millimeters. So one of the first things we're going to work out then is area. So in finding out the area, we need pi r squared. So the radius is half of the diameter. So therefore I've just half the diameter, but I've also, because I need my area to be in meters squared, I've put it in terms of millimeters in the first place, so times 10 to the minus 3, so my result that I get will be in meters squared. Okay, so there we have that bit. So now we can then put everything into the equation that we know. So we've got resistance, we know the resistivity of the wire, 22 times by 10 to the minus 8, and we know that it's 2.8 meters long, so therefore, and then we can divide it by our area, and if we put all of that into our calculator, we should then get ourselves 2.5 ohms. Okay, straightforward enough. Okay, so shall we just do another one where we've actually, maybe we're finding out the resistivity of the cable. Okay, so in this example we've got 2 meter length of wire, diameter again we're given, so one of the first things we're going to do is convert our diameter to radius so we can calculate the area. So race ahead. Okay, so there we have it, 384.84 times 10 to the minus 9 meters squared. Yeah, it's just my preference. I like to convert my stuff into meters in the first place, so we've got 0.35 times 10 to the minus 3. If you want to do it afterwards, then that's up to you, but it's just my personal preference. So then we can put what we know then into our formula for calculating resistance using resistivity before we start doing any rearrangements. Okay, so I've just put all my stuff in. So the first thing we can do is we can bring our area across. Okay, and we'll just take it from there. I like to do my rearrangements a little bit at a time. If you're a bit more confident, then you can obviously do it a bit more than that, but I just do it one step at a time. Okay, so almost made a mistake there myself. So 0.5 times by 384.84 times 10 to the minus 9. So multiply them together. So it brings that across onto this side, is equal to the resistivity times 2. So then, therefore, I can divide all of that by 2. Gives me my resistivity figure of 9.21 times 10 to the minus 8 ohms per meter. Done. So we're going to finish off this video by just looking at temperature coefficient. So let's remind ourselves of the temperature coefficient formula. So our temperature coefficient, the actual temperature coefficient value that we get is mixed in with the formula. So we've got a change in resistance. The delta R divided by the original resistance is equal to the temperature coefficient multiplied by the change in temperature. So if we look at this example here, then our change in resistance that we've got is going from 1 ohm to 5 ohms. So the change in resistance that we've got is 4 ohms divided by our original resistance, which is 1 ohm, is equal to our temperature coefficient that we're looking to find, and then delta T, so the change in temperature looks like it's going to be 10 degrees. So there we have it, 0.4. 4 divided by 1, and then divide the whole thing by 10. So our temperature coefficient is 0.4. It is 0.4 per degrees see, but quite often you'll see it without any units at all. So I'm just going to leave it as is. And that will do us, I think, for this video altogether. There's not a lot more we can really say about our temperature coefficient, really. Yeah, okay, we could look for looking find original resistance or whatever, but straightforward. Yay!